Hello, everyone. I would like to start by acknowledging my co-author and advisor, Dr. Hans-Peter Schaub. So today I'm going to talk about relative motion from a spinning chief body frame. Usually when we model the relative motion of two spacecraft, a chief and a deputy around Earth, for example, we use a chief-centered hill frame. And this frame is aligned with respect to the orbit of the chief. In this frame, we have formulations that allow us to directly model the relative motion there. But in the final phases of approach, we're also interested in the structure of the chief because this introduces keep-out zones to avoid collision, as well as keep-in zones for dock-in operations, in-orbit servicing, or just inspection. These zones translate into constraints for motion planning. And since we're using a frame that's aligned with the orbit and not the structure, these constraints are usually time varying, which complicates the motion planning process, especially if the chief is spinning. So in this paper, we wanted to consider using the body frame instead, where the constraints are constant, and investigate how would this relative motion look like from its perspective. Let's start with the motion in the hill frame. The advantage of the hill frame is that it offers a variety of analytical solutions that allow us to directly propagate the relative motion without the complexity of numerical integration. A well-known example is the CW equations that consider circular chief orbits, such as GEO, which is a prime target for in-orbit servicing. Their analytical closed-form solution here intuitively describes the shape of the motion using a set of 6 elements. Looking at the equation, we can see that the shape describes a 2x1 ellipse in the xy plane. The amplitude is governed by the element A naught, and this can also be offset according to the element y off. The out-of-plane motion is decoupled. It's a simple harmonic oscillation with amplitude B naught. And then we have the two angles, alpha and beta, that define the phase offset in plane and out of plane. Finally, the element x off is due to a difference between semi-major axes between both axes. So this leads to this long track drift in the hill frame and therefore unbounded motion trajectories. Prior work by Hamel and Schaub has studied the relative motion from the perspective of a chief-centered inertial frame. So in this case, the axes have a fixed orientation. And in their work, they derived a new set of elements that also give the shape of the motion in this frame an intuitive description. This is interesting because this corresponds to the body frame of an inertially fixed satellite. And in this work I'm presenting today, we wanted to expand on this by considering that the chief is also spinning. So in this case, the inertial frame and the body frame are not aligned. To get the equation of motion in the body frame, we start from that in the hill frame, and then we map it using a DCM. To get this DCM, we need to know the dynamics of the spacecraft, so meaning how it's spinning. And this obviously depends from case to case. So in this paper, we decided to focus on a subset of cases where the body frame is initially aligned with the hill frame, and we consider 3 primary spin cases. So with a constant angular velocity about 1 axis at a time. If it's spinning about the orbit normal direction like this, we have the other 2 axes that remain in the same plane. So the DCM corresponds to the rotation matrix about the 3rd axis. When we plug this into the equation on top, we get this equation. So along the z-axis, it doesn't change, but in the xy plane, it's not really intuitive. Looking at this, we wouldn't know what shape it has. And actually, this shape depends on the ratio of omega, the angular velocity, to n, the orbit rate. When omega is equal to n, so when the spacecraft is spinning with 1 revolution per orbit, for example, if it's maintaining Earth pointing as it rotates, we have shapes looking like this. And these shapes actually correspond to epitrochoids, which is a path traced by a point attached to a circle, rolling without a slip outside another circle. Unlike the ellipse in the hill frame, this can also be characterized using a set of 4 elements. The first one is r, the radius of both circles. Then we have d, which is the arm length, the distance between the center of the rolling circle and the point of which we're tracing the circle, which is the deputy in this case. Then we have alpha that defines the orientation of the curve in plane. And finally, phi is the phase offset between both circles. Knowing that that's the shape we have, we can rewrite the equation to this form, which is the parametric equation of an epitrochoid using the elements I just presented that we derived from the linearized relative orbital elements. Let's dig more into the shape. So when we have unbounded bounded motion, so x off is equal to 0, or elements are constant, and phi is always equal to 0 in this case, and r is only a function of y off. So when we change that, we change the radius, and with that, we change the size and the shape of the trajectory. The same thing happens when we change A naught, and with that d, because this shape and size depends on the ratio of r to d. Changing d actually also changes the offset between the center of the formation and the chief. Then we have alpha that defines the orientation of the curve in the plane. And if the motion is unbounded, two elements become time varying, and this leads to this drift of the epitrochoid pattern, either outwards like this or inwards, depending on the sign and the norm of x off. So the analytical solution for the equation of motion in the body frame exists if we know the DCM, whether it is in this form or in this one. So the main contribution or goal here is to get this new set of elements that gives the shape a more intuitive interpretation. Using these elements, we can tell a lot about the position of the chief with respect to the body, the deputy with respect to the chief. We can, for example, tell its proximity from key body axis or the potential to remain within a certain region around the chief, or even to find a drift towards a certain point or towards the chief itself. These are important information that we cannot extract directly from the first equation, and this is the whole point of this new formulation. With that being said, I want to talk about the case when omega is not equal to n. This leads to different cases. And this is an example. What we see here is still a trochoidal curve. So it's still in the same family as epitrochoids, but we see an alternation of smaller and larger loops. And this is actually due to the fact that the elements that describe the shape are time varying. In this case, what I notice is that we lose this intuitive interpretation of the elements with a lot of time variations. So in this case, we decided to focus on finding certain geometries that will allow us to find shapes that can be described using invariance of motion. And in the case of orbit normal spin, it's when both x off and y off are equal to 0. So when omega is equal to n, we have these shapes, and these shapes actually correspond to hypotrochoids, which are paths traced by a point attached to a circle, rolling inside another circle this time. And like epitrochoids, we can also describe them using a set of 4 elements, the radii of both circles, g the arm length, and alpha the orientation. And in this case, we don't have an offset because the path is centered around the chief. Going back to the results, so these different shapes we have are due to different ratios of both radii. The size of the orbit depends on the element on the arm length, g, and the orientation on the angular element, alpha. When omega is larger than n, we're back to epitrochoids. The one on the left is exactly like the ones I presented earlier, and the other ones are also epitrochoids, but they are a result of circles of different radii. So this shape depends on their ratio, which is directly associated to n over omega. The size is also a function of the arm length g and the orientation of alpha. So we did these same derivations with the other 2 cases I mentioned earlier about the radial and along track directions. And what we notice here is the pattern. So when omega is equal to, smaller than, or larger than n, we have the same shapes for all 3 cases. But these shapes are described more like the definition of the elements that describe these shapes are different from case to case, but also the geometry that gives us intuitive shapes when omega is not equal to n is also different for each case. If you're interested to know the details of their description of the elements, I invite you to take a look at our paper. So to conclude, we investigated the relative motion from the perspective of a spinning sheaf body frame. We based the derivations on the CW equations, so they are applicable to circular sheaf orbits or near circular. We considered three primary spin cases with constant angular velocity. We have considered a hill frame that is initially aligned with, or the body frame initially aligned with the hill frame, rotating about one principal axis at a time. All of these three axes cases has led to three subcases in terms of shapes, depending on the ratio of omega to n. So we have found epitrochoids or hypotrochoids in general. In specific cases, they can reduce to circles. For each of these cases, we have derived orbital elements that give the shape a more intuitive aspect. This new description allows us to characterize the equation of motion directly from the body frame of a deputy. We can tell a lot about the shape and the aspect of the trajectory there, and even plan a maneuver directly in the body frame, especially if we extend this work to variational equations of motions for these elements. Thank you for listening to my presentation, and if you have any questions, please reach out.